For most of human history, we believed the universe was simple, predictable, understandable. We thought the cosmos was a grand clock, ticking with perfect regularity, governed by rules that humans could eventually decipher if only they looked closely enough. But every time we thought we understood it, every time we believed we had reached the final truth, the universe revealed something new, something stranger, something that shattered everything we thought we knew. This is the real story of science, not a steady march toward certainty, but a constant process of being proven wrong over and over again. And the most astonishing part is this: every mistake humanity has made about the universe did not shrink our understanding. It expanded it. The universe kept growing bigger, older, deeper, and more mysterious. And we realized that our assumptions were not just wrong, they were too small. Our imagination was too limited. Our expectations were too narrow for a universe built on strangeness. To understand why we were wrong, we have to go back to the earliest days of human thought. The cosmos felt small then. The sky was a ceiling dotted with lights. The stars were fixed. The earth was the center of everything. The sun and moon circled us like attendants in a cosmic palace. It was a comforting belief. It gave humans a clear place in the universe. But it was wrong. When Copernicus suggested the Earth wasn't the center, people resisted. The idea felt too big, too destabilizing. But the truth couldn't be ignored. The Earth was just another planet orbiting the sun, and even that was only the beginning. Centuries later, humans believed the sun was the center of everything. After all, the sun lit our world, warmed our oceans, created life. It felt natural to assume it was the center of the cosmos, but we were wrong again. The sun was merely one star among countless others, drifting in a galaxy so vast that it would take hundreds of millions of years to cross. And when we finally understood that even the galaxy wasn't the whole of reality, but just one island among billions, the universe suddenly felt impossibly large. Every correction humbled us, but it also expanded the boundaries of what we could imagine. Yet even these were just the early mistakes. The deeper errors came later. Errors that revealed not just the size of the universe, but the nature of reality itself. For a long time, we believed space was a simple emptiness, a backdrop, a void, a nothingness between stars and planets. But we were wrong. Space is dynamic. It curves, stretches, bends, twists. This discovery came from a mind few could match, a patent clerk who imagined beams of light and falling elevators until the universe itself revealed its secrets. When Einstein introduced the idea that gravity wasn't a force but the curvature of space-time, the universe suddenly became fluid. Not static, not rigid, but alive in a sense. Space could ripple, time could stretch, mass could warp the path of light. And the bigger shock came later when we realized this cosmic fabric wasn't stable. It was expanding. But we misunderstood even that at first. Humans assumed expansion meant galaxies were flying through space, but they weren't. Space was expanding itself. The universe wasn't drifting into something bigger. It was creating more space as it grew. And we were wrong yet again when we thought this expansion would slow down. Gravity was supposed to pull everything back together. Instead, the expansion is speeding up. Something unknown, something we still cannot explain, is pushing the galaxies apart faster and faster. We call it dark energy. But the truth is, we have no idea what it is. Being wrong is not unusual in science, but being wrong this often, this profoundly, suggests something deeper. Our intuition is simply not built for a universe like this. We believe time flowed like a river, smooth, constant, universal. But we were wrong. Time speeds up and slows down depending on gravity and motion. Time passes more slowly near massive objects. It passes more quickly in empty space. And perhaps the biggest revelation was that time is woven together with space. The universe isn't made of separate ingredients like time, energy, and matter. They are intertwined. They form a single dynamic entity. This means that our most basic experiences, the passage of time, the feeling of a moment, are shaped by the physical structure of the universe. And this realization led to an even more radical idea. There may be no universal now. There is no single moment that exists everywhere at once. The present is relative. What you consider the present depends on where you are and how fast you move. Even the idea of before and after breaks down at the edges of physics. Our mistake was believing time was absolute, but it is not. We were wrong about stars, too. Early scientists believed stars were eternal, that they burned forever. But stars are mortal. They are born in clouds of dust, shine for millions or billions of years, and then die spectacular deaths. Some collapse into black holes, regions where gravity is so extreme that space and time fold into impossible shapes. Others explode as supernovae, seeding the universe with heavy elements needed for planets and life. We were wrong about how big stars could be, wrong about how long they could live, wrong about how they formed, wrong about how they died. Every correction revealed the universe was more dramatic than we had ever imagined. We were wrong about the age of the universe. At first, scientists believed it was only a few billion years old. Then we realized it was much older, about 14 billion years. That alone shattered assumptions, because it meant the universe had a beginning, a moment when everything, space, time, matter, energy, emerged from a single point. But we misunderstood that too. We pictured the Big Bang as an explosion. But there was no explosion, no outward blast. Instead, space itself expanded. The universe grew from a hot, dense state, not by erupting into space, but by creating space. Even now, we're not sure what the Big Bang really was. It might not have been the beginning of everything. It might have been a transition, a bounce, a phase change, a doorway. We once believed there was nothing before it. Now, some theories suggest there might have been infinite universes before ours, or that the Big Bang was the collision of higher dimensional structures, or that the universe is part of an eternal cycle. We were wrong to think the universe was simple, but in being wrong, we uncovered deeper truths. Then came the greatest errors of all, dark matter and dark energy. These two mysteries forced us to admit that everything we see, everything we touch, everything we know, is only a tiny fraction of what exists. The stars, planets, galaxies, dust clouds, nebulae, all the luminous matter make up a small slice of the universe's content. Most of the universe is invisible. Dark matter shapes galaxies, dark energy shapes the cosmos as a whole, and we cannot see either one. We do not know what they are. We only know they exist because their effects are undeniable. We were wrong about what the universe is made of. Most of it is unknown, and we may be wrong about even more. Some physicists believe gravity itself may not be what we think it is, that the universe may have hidden dimensions that we cannot perceive, that reality might be holographic with everything we experience projected from a deeper informational layer. We might be wrong about space, wrong about time, wrong about the laws of physics themselves. But every mistake leads us deeper into truth. Perhaps the greatest correction humanity has made is this. We were wrong to think the universe is understandable in human terms. The universe is not obligated to match our intuition. Reality is not required to be comfortable. The cosmos is not built for our convenience. It is vast, strange, ancient, and indifferent, but it is also beautiful. What's even more astonishing is that the universe does not resist being understood. It rewards our curiosity. Every time we question our assumptions, every time we throw out old ideas, every time we admit we were wrong, the universe opens a new door, a new mystery, a new layer. And what lies beyond those layers is still unfolding, still surprising, still rewriting everything we thought was true. We were wrong about the Earth's place, wrong about the sun, wrong about the galaxy, wrong about the shape of space, wrong about the flow of time, wrong about matter, wrong about energy, wrong about the beginning, and we will be wrong again. But each correction brings us closer to understanding the truth, a truth that is bigger, deeper, and more astonishing than anything we have ever imagined. And perhaps the most important revelation of all is this: the universe is not done surprising us. We are not at the end of knowledge. We are at the beginning. We are standing in the earliest dawn of cosmic understanding. And with every discovery, the universe whispers something new, something humbling, something thrilling. We were wrong. But that is why we keep moving forward. Being wrong is not a failure. It is the engine of discovery. It is the fuel of science. It is the reason we continue to explore. Because the universe is not what we thought. It is far more wondrous. And the questions we ask today will seem small compared to the questions we ask tomorrow. For centuries, humanity believed the universe was shaped like a perfect sphere, smooth, symmetrical, elegant. It was an idea that comforted us, that fit the way we wished reality to be. Perfection, harmony, balance. The cosmos, we imagined, was a flawless creation, maybe even designed to be that way. But as always, the universe had other plans. We were wrong about its shape. Not just a little wrong, completely wrong. The true shape of the universe turned out to be far stranger, far more complex, and far more mind-bending than anything ancient philosophers or even early scientists could have imagined. Because the universe is not a smooth sphere, it is not a perfect bubble, it is not even a consistent geometry. Instead, it is an ever-shifting, dynamic, warped fabric where straight lines are illusions and curvature is everywhere. Our first mistake was assuming space was flat. When we look across a room, the floor appears flat. The horizon appears straight. Space seems like an empty container, a simple background where planets and stars drift. For most of human history, that assumption seemed obvious. But we were wrong. Space is not a flat stage. It is a living, flexible structure that bends and curves depending on the mass and energy within it. The shape of the universe is determined not by aesthetics or intuition, but by gravity itself. The first cracks in our assumptions appeared when Einstein introduced the idea that gravity is not a force, but the curvature of space-time. Mass tells space-time how to curve. Curvature tells mass how to move. Suddenly, straight lines were no longer straight, space was no longer flat, and the universe was no longer a geometrically simple object. It was a warped, dynamic surface where the very idea of a straight path becomes ambiguous. Light, which always travels in straight lines through space, appears to bend around stars because space itself curves. This was our first clue. But we continued to underestimate just how warped the universe really is. When scientists began studying the large-scale structure of the cosmos, they discovered something astonishing. Matter is not spread evenly. Galaxies are not arranged in a smooth pattern. Instead, they are arranged in a cosmic web, vast filaments stretching across the universe, separated by huge voids of empty space. Imagine a sponge, or the froth on top of boiling water. Filaments of galaxies form the sponge's structure, while the empty regions are the holes. That is the true shape of the universe on a large scale. A cosmic web, not a sphere. A universe woven from threads of galaxies, clusters, and superclusters, stretching over unimaginable distances. And even this cosmic web is only the beginning. The shape of the universe is determined by its curvature. There are three main possibilities. It could be flat, positively curved, or negatively curved. For a long time, scientists believed the universe might be positively curved, like the surface of a sphere. This would mean the universe is finite, with no edges. If you traveled far enough in one direction, you would eventually return to your starting point, just as a traveler walking around the Earth eventually ends up where they began. This idea was comforting. It gave the universe order. But the universe is not here to comfort us. When scientists measured the cosmic microwave background radiation, the faint afterglow of the Big Bang, they expected to find evidence of curvature. They expected to detect the universe's shape. But the measurements revealed something stranger. The universe appears to be extremely close to flat, but not exactly flat. It is so close to flat that it is almost impossible to tell whether it is truly flat or just very slightly curved on scales too large for us to detect. This was our second mistake. Assuming the universe's shape could be easily measured, the true curvature of the universe may be so subtle, so faint, that even with our most precise instruments, we cannot detect it. Imagine standing on an enormous sphere so large that the curvature is invisible. Everything around you appears flat, even though the surface curves ever so gently. That may be our universe, extremely close to flat, but curved in ways we cannot yet see. But the story becomes even stranger when we consider higher dimensions. If the universe exists on a three-dimensional brane floating within a higher dimensional bulk, then the shape we perceive is not the full shape. The universe may be curved in directions we cannot perceive, just as a two-dimensional creature on a sheet of paper cannot perceive the paper bending upward or downward. The creature believes the universe is flat, but we see the curvature because we exist in a higher dimension. In this sense, our belief that the universe is flat may itself be an illusion created by our limited perception. And then came one of the most surprising discoveries of all time. The universe is expanding. Not only expanding, but expanding faster and faster. This expansion affects the universe's shape in profound ways. If the expansion continues indefinitely, the universe may be open and infinite, stretching outward forever like a saddle-shaped surface. If the expansion slows down and eventually reverses, the universe may be closed like a sphere, curving back on itself. If the expansion continues at the exact rate needed to treat balance curvature, the universe remains flat. The true shape depends on the ultimate fate of the cosmos, and because we do not yet know how dark energy behaves, we do not know the universe's final shape. This means that the universe's geometry is not fixed. It is dynamic, changing, evolving. The shape of the universe is a story, not a static structure. But the greatest surprise was still to come. We discovered that the universe might not have a global shape at all. The idea that the entire universe has a single simple curvature may itself be wrong. Space-time could be curved differently in different regions. The universe could contain pockets of positive curvature, pockets of negative curvature, and vast regions of near flatness. On the largest scales, the universe could be a patchwork of geometries. This shatters the notion of a tidy, symmetrical cosmos. The more we studied the universe, the more bizarre possibilities emerged. Some scientists proposed that the universe might be shaped like a torus, a donut shape, where space loops around in complex ways. In such a universe, traveling in a straight line long enough might cause you to return to your starting point from an unexpected direction. Other theories suggest the universe could have a shape similar to a higher dimensional hypercube, or that space might be multiply connected, meaning distant regions of the universe could actually be the same region, connected through hidden pathways in space-time. Imagine walking through a hallway and suddenly finding yourself at the end of the same hallway without ever turning around. That is what a multiply connected universe could look like. The universe could be smaller than it appears, but warped in such a way that distances fold onto themselves. This is not science fiction. These are serious mathematical possibilities explored by cosmologists studying the topology of space. And then we discovered something even more shocking. The universe may not be three-dimensional at all. Instead, it may be two-dimensional at the deepest level, with the three-dimensional reality we experience emerging as a projection, a hologram. If the holographic principle is correct, then the idea of the universe having a traditional shape becomes meaningless. The universe's shape would not be a physical object. It would be a geometric encoding on a cosmic boundary, a mathematical surface where information is stored. This flips everything we believed about the universe upside down. We thought we lived inside a three-dimensional world, but we might be living inside a projection of deeper two-dimensional physics. In this picture, asking about the shape of the universe is like asking about the shape of a movie screen. The shape of the screen matters far less than the information encoded on it. And then comes another theory, that the universe is shaped not by classical geometry, but by quantum geometry. On extremely small scales, space-time is not smooth. It is grainy, jagged, chaotic, a foam of constantly fluctuating shapes. In this quantum foam, the very concept of shape dissolves into probability. The universe does not have a single shape. It has countless possible shapes, constantly emerging and fading. We were wrong to think the universe is smooth. It is jagged, broken, wild. But perhaps the greatest mistake of all was believing the universe's shape could be described in simple terms at all. Every time we tried to put the universe into a neat geometric box, it resisted. Every time we tried to simplify it, it expanded in complexity. Every time we declared, "Now we understand," it revealed another layer. The shape of the universe is not a sphere, not a flat plane, not a saddle, not a donut, not a hypercube, not a hologram, not a quantum foam. It is all of these and none of these, because the universe is not a static object with a rigid shape. It is a dynamic, evolving geometry shaped by matter, energy, and space-time itself. The universe is an unfolding, a process, a living fabric whose shape is defined not once, but constantly. And this realization changes everything, because it means we cannot draw a boundary around the universe. We cannot point to a shape and say, "This is what it is." Every shape we imagine is too small, too limited, too human. The universe is stranger than geometry. It is stranger than mathematics. It is stranger than thought. And that is why we keep being wrong, not because we are foolish, but because the universe is too vast, too complex, too creative to be captured in simple forms. We were wrong about the shape of the universe, and in being wrong, we discovered something far more beautiful. The universe is not a shape. It is a story. For most of human history, we believed empty space was exactly what the phrase suggests: nothing, a void, a cold, mute absence between objects, a meaningless gap between planets and stars. But this belief, like so many others, crumbled the moment we learned to look deeper. Because the vacuum is not empty. The vacuum is not silent. The vacuum is not lifeless. It is the opposite. Empty space is one of the most active, vibrant, chaotic arenas in the universe. It is a place of ceaseless motion, endless energy, hidden activity, and unimaginable potential. In many ways, the vacuum is more alive than the matter floating inside it, and our misunderstanding of it reveals something important about the human mind. We mistake invisibility for nothingness. We assume that if something cannot be seen or touched, it must not exist. And yet the universe hides its most powerful secrets in the places that look the most empty. To understand how wrong we were, imagine stripping away every particle, every atom, every photon, every molecule. Imagine removing all the dust, all the radiation, all the fields, all the matter. What is left? For centuries, humans believed the answer was a perfect nothing, a quiet, passive void. But the universe is not that simple. Even in the most perfect vacuum imaginable, a vacuum purer than anything humans can create, space seethes with activity. It boils with quantum fluctuations. It hums with zero-point energy. Particles appear and vanish faster than any eye could ever track. Waves ripple without anything to carry them. Fields fluctuate even when no force acts on them. Space behaves less like emptiness and more like a restless ocean. This revelation was one of the most shocking discoveries in physics. It shattered our intuition, it shattered our comfort, and it revealed that reality is far stranger than we were prepared to accept. The idea first emerged from quantum mechanics, when scientists realized that particles do not exist in fixed positions, but instead behave like waves spread out through space. A particle's position is a probability, not a certainty, and probability never reaches zero. That means even in empty space, the wave functions of possible particles ripple and vibrate. The vacuum can never be perfectly still. There will always be fluctuations. These fluctuations cause pairs of particles to appear from nothing and vanish back into nothing in unimaginably short intervals. These pairs are called virtual particles, a name that sounds fictional but describes one of the most fundamental properties of the universe. These virtual particles are not just theoretical curiosities, they have real effects. They create measurable forces, they influence the behavior of atoms, they affect the expansion of the universe itself. Empty space, it turns out, is not a blank canvas. It is the paint, it is the brush, it is the medium of creation. One of the first clues that the vacuum was alive came from the Casimir effect, a strange phenomenon in which two metal plates placed extremely close together are pushed toward one another, even though there is nothing between them. For decades, scientists puzzled over this mysterious force until they realized the plates were not being pushed by nothing. They were being pushed by the vacuum itself. The plates block some wavelengths of virtual particles between them, but outside the plates, all wavelengths are allowed. This imbalance in quantum fluctuations creates pressure, pushing the plates together. The vacuum is literally squeezing the metal with invisible hands. If empty space can push objects, then empty space is not empty. But the story grows deeper, because the vacuum contains not only virtual particles, but also quantum fields, the fundamental ingredients of reality. In quantum field theory, every particle is a vibration of a field. There is an electron field, a photon field, a quark field, a Higgs field. These fields are everywhere, including in empty space. They do not disappear when matter disappears. They remain, humming softly at their lowest energy state. The vacuum is a sea of fields at rest, but rest does not mean zero. Even at their lowest state, they vibrate. This constant, unavoidable vibration is called zero-point energy. Zero-point energy is the ground state of the universe, the baseline hum of existence. If the vacuum had absolutely zero energy, the fields would be perfectly still. But perfect stillness is forbidden by quantum mechanics, so the vacuum always contains energy. And this energy has consequences. The greatest of these consequences is dark energy, the mysterious force accelerating the expansion of the universe. Many scientists believe dark energy may be linked to the energy of empty space itself. That means the vacuum is not just active, it is pushing the universe apart on cosmic scales. What appears empty is actually full of energy, strong enough to reshape the cosmos. We were wrong about the vacuum. It is not nothing, it is everything. But the vacuum hides even more secrets. One of the strangest discoveries in physics is that empty space has structure. Space can stretch, it can compress, it can twist, it can ripple. These ripples, gravitational waves, pass through the vacuum like vibrations through a vast invisible fabric. When two black holes collide, they create ripples so powerful they stretch space itself, like a drumskin hit by the universe's most ancient hands. These waves travel through empty space effortlessly. They do not need air. They do not need matter. The vacuum itself carries the waves. If empty space were truly empty, gravitational waves could not exist. Then there is the Higgs field. This field permeates all of space. It gives mass to particles. Without the Higgs field, electrons would have no mass, protons would not form, atoms would not exist, stars would not shine, life would never emerge. The Higgs field is everywhere, even in regions where there is no matter. It is the invisible glue that allows the universe to take shape. Without it, the vacuum would be a meaningless void incapable of supporting structure. Because of it, the vacuum becomes a cosmic foundation. We were wrong to think the vacuum was passive. The vacuum is the architect of matter. Then we learned something even more shocking. The vacuum may contain entire universes. In some versions of inflation theory, our universe began as a fluctuation within a larger vacuum. Tiny regions of high energy expanded rapidly, forming pocket universes, bubble universes, each with its own laws of physics. In this picture, the vacuum is not emptiness. It is a field of infinite potential, constantly spawning new universes like foam, bubbling at the edge of existence. This idea is not fantasy. It is a serious scientific proposal supported by the mathematics of inflationary cosmology. If true, it means empty space is not simply alive, it is creative. But perhaps the most mind-bending idea of all is the concept of vacuum decay. The possibility that the vacuum is not in its lowest possible state. The universe might be sitting in a false vacuum, a metastable energy state. If so, it could collapse into a lower energy state at any moment, rewriting the laws of physics in an instant. This transition would destroy the universe as we know it, not through explosion, not through heat, not through cold, but through transformation, a shift in the underlying fabric of space. It is a terrifying idea. But it also reveals something profound. The vacuum is not static. It is dynamic. It evolves. It contains phases, levels, states, and transitions. The vacuum is a medium with properties as complex as any material we have ever studied. Calling it empty is like calling an ocean dry because you cannot see the water molecules. We were wrong about the vacuum because we trusted our senses. We believed that if something looked empty, it must be empty. But the universe does not reveal its secrets to the naked eye. The most important structures in reality are invisible. Fields, particles, waves, forces, energy states, quantum fluctuations. The universe is built not from objects, but from interactions, not from shapes, but from relationships, not from matter, but from fields. And empty space is where these relationships live. What we once dismissed as nothing turns out to be the foundation of everything. The vacuum holds the scaffolding of physics. It holds the seeds of galaxies. It holds the fluctuations that shaped the early universe. It holds the energy that drives cosmic expansion. It holds the fields that give matter its properties. It holds the possibilities from which new universes arise. The vacuum is not an absence. It is the womb of reality. And our mistake was not simply misunderstanding empty space. Our mistake was assuming simplicity where there was complexity, assuming silence where there was activity, assuming nothingness where there was creation. We were wrong about the vacuum because we underestimated the universe. We assumed the cosmos would be intuitive, familiar, understandable, but nothing about the universe is intuitive. The universe is not simple. It is not obvious. It is not gentle. It hides its greatest secrets where we least expect them. And the vacuum, the place we once thought was empty, may be the most powerful, dynamic, creative substance in existence. For as long as humans have existed, we've lived inside the flow of time. It feels linear. It feels constant. It feels inescapable. A steady current that pulls us from birth toward death, from past toward future, from what has already happened toward what has not yet arrived. Time feels like the most fundamental truth of existence. It is the rhythm of our lives, the heartbeat of experience, the invisible river that carries everything forward. But as with so many ideas we once took for granted, we were wrong about time. Terribly wrong. The more deeply we looked into the universe, the more time unraveled. It bent, it warped, it slowed, it sped up, it fractured. It behaved in ways no human intuition could ever predict. And eventually, the truth became unavoidable. Time is not what we think it is. It is not absolute. It is not universal. It is not constant. It is not even fundamental. Time is flexible, relative, emergent, and possibly even illusory. Our first mistake was assuming that time flows the same for everyone, everywhere. For most of human history, this belief seemed obvious. A second is a second. A minute is a minute. A day is a day. But the universe does not care about our clocks. Time depends on motion. Time depends on gravity. Time depends on the shape of space itself. The idea that time is universal collapsed when Einstein rewrote the rules of reality. He showed that time slows down for objects moving at high speeds. If you travel fast enough, time stretches. Seconds become longer. Minutes become longer. Hours become longer. A person traveling near the speed of light ages far more slowly than someone standing still. Two twins could live completely different amounts of time simply by following different paths through space. This was the first deep fracture in our understanding. Time, the most absolute thing we knew, turned out to be relative. But relativity was only the beginning. The next revelation was even stranger. Gravity bends time itself. The stronger the gravitational field, the slower time passes. This means that clocks tick more slowly on the surface of a planet than in deep space. Time passes faster on mountaintops than at sea level. Time passes more quickly for satellites orbiting the Earth than for people on the ground. These effects are not theoretical. They are measured every day. Global positioning systems must account for these distortions, or they would drift by miles each hour. The devices we use to navigate rely on the fact that time does not flow the same everywhere. We were wrong to think time is universal. It is not. Time is personal. But the deeper we looked, the stranger the story became. Time is not separate from space. They are intertwined. They form a single unified entity, space-time. This fusion means time is not a backdrop. It is not independent from the universe. It is a dimension woven into the fabric of existence, and space-time can be stretched, squeezed, curved, and twisted. When space bends, time bends. When space stretches, time stretches. When mass shapes space, it shapes time. This means the shape of the universe shapes the flow of time. Time is not merely something that happens, it is something that is shaped. This alone would have been shocking enough. But then physicists realized something even more unsettling. The flow of time may not be real. The passage of time, the feeling that moments move from past to present to future, may be an illusion created by consciousness. The laws of physics at their deepest level do not distinguish between past and future. They are time-symmetric. They run the same in both directions. Nothing in the equations of quantum mechanics or general relativity requires time to flow. Time appears in the equations as a dimension, not as a moving river. This raises a terrifying possibility. The past, present, and future all exist simultaneously. Time does not move. We move through time. And then came an even more astonishing idea. The universe might be a block, not a dynamic evolving structure, but a four-dimensional block where every moment, from the birth of stars to the end of the cosmos, is frozen in place. In this block universe, time is a landscape. You can walk through it conceptually the way you walk across terrain. The present is simply the slice of the landscape where your consciousness happens to be. Yesterday still exists. Tomorrow already exists. The future is already written in the fabric of space-time. This interpretation challenges everything about human experience. We feel time flowing. We feel moments passing. We feel ourselves aging. But the block universe tells us this flow is subjective, a phenomenon generated by our consciousness moving across a timeless structure. Our sense of time may be a feature of the brain, not a feature of reality. We were wrong to believe that the present is unique. The universe does not have a universal now. But the story of time becomes even more bizarre when we look at black holes. At the edge of a black hole, the event horizon, time slows to an absolute crawl. For someone falling in, time appears normal. But to an outside observer, the falling person slows until they freeze. Their final moment stretches into eternity. In this sense, black holes are time machines. They distort time so dramatically that the universe behaves differently near them. We once believed time was a consistent backdrop, but black holes show that time can nearly stop. And near a singularity, the point of infinite density inside a black hole, time may cease to have any meaning at all. Then we discovered something even stranger. In the early universe, time may not have existed. Time may have emerged after the Big Bang the way bubbles emerge from boiling water. Before that, there may have been no past, no future, no before. Time may be a property of an expanding universe, not a fundamental ingredient. This means time could end. If the universe reaches a maximum entropy state, time may lose its directionality. The arrow of time, the feeling that things move from order to disorder, arises from entropy. If entropy stops changing, the arrow may stop. Time could fade away. This idea feels impossible. How can time vanish? How can a universe exist without time? But quantum cosmology suggests exactly this. Time may not be built into the universe. It may be built into us. Then comes quantum mechanics, a realm where time behaves in ways even stranger than relativity. Quantum particles can become entangled, sharing information instantly across vast distances. This instantaneous connection seems to violate the flow of time. It does not care about past or future. It does not obey classical causality. Entanglement suggests that time may not be fundamental. Instead, it may emerge from deeper principles of information. Some physicists propose that time arises from quantum entanglement, that time is secondary. That time is not a basic ingredient of the universe, but a byproduct of how systems become correlated. If true, time is not woven into the universe. Time is woven by the universe. We were wrong to believe time is required for existence. Existence may create time. But perhaps the most shocking idea of all is this: the laws of physics themselves do not require time to flow forward. The forward flow of time, the arrow pointing from past to future, arises from entropy, not from any deep physical law. If you reverse the positions and velocities of every particle in the universe, the equations allow the universe to run backward perfectly. The only reason we experience time moving forward is because the universe began in a low entropy state. The arrow of time is not absolute, it is environmental. It is dependent on initial conditions. This implies something devastating. The future may be as fixed as the past. We move through time, but time does not move through us. If all this were not strange enough, the universe delivers a final blow to our understanding. Experiments in quantum foundations suggest that the future can influence the past. This idea, known as retrocausality, implies that events have connections that do not respect temporal order. It suggests that causality may run both directions, that the future may help shape the past just as the past shapes the future. This undermines our most basic assumption, that time flows from before to after. In some interpretations, the universe settles into a configuration that is consistent across time, rather than following a simple forward progression. The universe may be a self-consistent loop of cause and effect, so we were wrong about time in every possible way. We were wrong about its flow, wrong about its constancy, wrong about its universality, wrong about its origin, wrong about its direction, wrong about its role in physics, wrong about its fundamental nature. But these mistakes were not failures. Each one revealed a deeper truth. Each one opened a new window. Each one expanded our view of reality. The universe does not move through time. Time is a dimension within the universe. The universe does not require time to exist. Time emerges from the universe. The universe does not evolve through moments. Every moment exists simultaneously. We were wrong about time. And in being wrong, we discovered something profound. Time does not shape the universe. The universe shapes time. For almost all of human history, gravity seemed simple. Apples fall, rain falls, people fall, everything falls downward. Gravity felt like the most familiar force in existence, the one part of nature we could always count on. Predictable, constant, universal, it pulled things together. It kept planets locked in orbit. It held the moon in its circuit around the Earth. Kept our feet on the ground. We thought we understood it so well that for centuries, no one even questioned its nature. But gravity was not what we thought. It was not a force in the way we imagined. It was not a simple pull. It was not the invisible magnet people assumed. It was something deeper, stranger, more flexible, and far more mysterious than we ever expected. And every time we tried to pin gravity down, it slipped through our fingers like smoke. We learned to predict its effects long before we understood it. We built scientific laws around it long before we realized how wrong we were about its essence. And the truth is that we are still wrong. Even today, gravity remains the least understood of all the fundamental forces. It is familiar, yes, but familiar in the way a shadow is familiar. We see its outline, but not the thing that casts it. Our first major misunderstanding of gravity began with Isaac Newton. He saw an apple fall, not the first person to witness such a mundane event, but perhaps the first to ask what force caused it. With astonishing brilliance, he formulated an equation describing how objects attract each other. Newton's law of gravitation explained everything from falling apples to the motion of planets. It predicted the tides, it predicted eclipses, it predicted the orbit of the moon. It predicted the dance of celestial bodies with incredible precision. It was a triumph so great that for centuries, people believed gravity was finally understood. Newton described gravity as a force, a pull that mass exerts on mass. And for a long time, that explanation felt complete, elegant, satisfying. But it was wrong. Gravity is not a force, or at least not in the way Newton imagined. It took another mind, Einstein's, to reveal what gravity truly is. and his revelation shattered the simplicity of Newton's picture. Einstein realized that gravity is not an invisible pull between objects. Instead, gravity is the shape of space-time itself. Massive objects bend the fabric of space-time, and that curvature guides the motion of everything within it. Planets orbit stars not because they are being pulled, but because they are moving along curved paths in a warped cosmic landscape. Light bends around stars not because gravity pulls on it, but because space itself curves. This idea was revolutionary. It transformed our understanding of the universe. Space was not an empty void. Time was not a steady river. The universe was a flexible, dynamic fabric woven from both. And gravity was simply the result of that fabric's bends and folds. But even Einstein's picture, as extraordinary as it was, turned out to be incomplete. It worked beautifully on large scales, planets, stars, galaxies. But the deeper we looked, the more cracks appeared. On the smallest scales, gravity refuses to behave. Quantum mechanics, the theory describing particles and forces at microscopic levels, does not know how to handle gravity. Every attempt to combine relativity and quantum mechanics has failed. Every attempt to quantize gravity, to treat it as a particle-based force, leads to infinities and contradictions. Gravity, unlike the other forces, resists unification. It stands apart as if it belongs to a different category of reality altogether. This is one of the biggest clues that we were wrong about gravity's nature. If gravity cannot be quantized, maybe it is not a force at all. Maybe it is something emergent, a phenomenon that arises from deeper principles, the way temperature emerges from countless molecular motions. Some physicists believe gravity may be an emergent effect of information, a byproduct of entropy, a consequence of how quantum fields store and distribute data. This idea is known as entropic gravity. If true, gravity is not fundamental. It is a shadow of deeper processes playing out on microscopic scales. We were wrong to think gravity is simple. It may be the most complex process in the universe. The next major error came when we discovered the behavior of galaxies. Based on everything we knew, galaxies should have torn themselves apart. The stars at their edges orbit too quickly. The gravitational pull of visible matter is not strong enough to keep them bound. Something was missing, something invisible, something providing additional gravity. This led to one of the greatest mysteries in science: dark matter. We do not know what dark matter is. We cannot see it. We cannot touch it. We cannot detect it directly. But we see its gravitational effects everywhere. It holds galaxies together. It shapes cosmic structures. It influences the motion of clusters. So we were wrong again. Gravity we observe is not caused only by matter we know. Most of it comes from matter we do not understand. But even dark matter failed to solve all the mysteries. When studying the expansion of the universe, scientists found something even stranger. The universe is expanding faster over time. This should be impossible. Gravity should slow expansion. But something is pushing galaxies apart, a repulsive effect that works against gravity. This unknown force was named dark energy. And suddenly, gravity's role in cosmic evolution became even more mysterious. Gravity is no longer the dominant actor on cosmic scales. It is challenged by dark energy, a force more powerful and more mysterious than anything we have ever encountered. We were wrong to think gravity controls the universe. It may be only one player in a far more complex cosmic drama. Then came the black holes. Objects so dense that space-time curves into a pit from which not even light can escape. Black holes are the ultimate expression of gravity. They are what happens when mass collapses so completely that the fabric of space-time tears. But black holes also break our understanding of physics. Inside them, Einstein's equations fail, the laws of physics collapse, space-time ends, and yet black holes radiate energy. They evaporate. They erase information, or perhaps preserve it in ways we do not yet understand. Black holes show that gravity reaches a point where it becomes unknowable, where our theories cannot describe reality, where a new theory, a quantum theory of gravity, is desperately needed. But what is quantum gravity? No one knows. We have guesses, hypotheses, hints. There is string theory, which proposes that gravity emerges from vibrating strings in higher dimensions. There is loop quantum gravity, which suggests that space itself is granular. There are holographic theories suggesting that gravity in 3 dimensions arises from information encoded on a 2-dimensional surface. Each theory offers glimpses of truth, but none is complete. We were wrong to believe gravity was understood. We understand its consequences, but not its essence. Even more astonishing is the possibility that gravity may not be uniform across the universe. Some theories suggest that gravity may vary with scale. It may behave differently in regions with different densities. It may weaken or strengthen depending on cosmic conditions. Modified gravity theories propose that dark matter and dark energy may not exist at all, that our equations for gravity are wrong on large scales. Perhaps gravity operates differently across billions of light years. Perhaps Einstein's equations need correction. Perhaps space-time behaves differently in the vast empty voids between cosmic structures. We were wrong to believe gravity is constant. Another layer of misunderstanding comes from time itself. Gravity affects time, but time also influences gravity. When space-time curves, time slows down. But when time behaves strangely, in quantum fluctuations, near black holes, or at the beginning of the universe, gravity becomes unpredictable. Gravity and time are not separate phenomena. They are entangled. They shape each other, and because we do not understand time, we do not truly understand gravity. We were wrong to separate gravity from the rest of physics. It is woven into everything. And then there is the possibility that gravity is the reason the universe exists at all. Tiny quantum fluctuations in the early universe created ripples in space-time. These ripples became seeds for galaxies. Without gravity, matter would never have clumped together, stars would never have formed, planets would never have emerged, life would never have appeared. Gravity is the architect of creation, but it may also be the architect of destruction. One day, gravity may tear apart space-time itself, or it may fade as dark energy takes over, or it may reverse, pulling the universe back into a cosmic collapse. We were wrong to think gravity is stable. It may have a history and a future just as dynamic as the universe itself. The truth is this: gravity is not simply the force that holds things together. It is the shape of existence, the curvature of reality, the architecture of cosmic evolution. And we understand only a fraction of it. Every time we think we understand gravity, it reveals something new, something deeper, something stranger. Gravity is not the familiar friend we thought. It is a mystery wearing the mask of familiarity. We were wrong, and we will be wrong again. Because gravity is not finished revealing its secrets. It is the doorway to understanding the universe, and perhaps the doorway to understanding reality itself. From the moment humanity first learned about the Big Bang, we imagined it as a grand explosion, a cosmic fireball erupting in the darkness, a beginning so violent and so explosive that it hurled matter outward to create everything we know. It was a comforting image in its own way, because explosions are familiar to us. They are dramatic, yes, but understandable. They have a center, they have a cause, they have a before and after. And so we built our mental universe around this picture, a single point exploding into space, igniting a chain reaction that sculpted galaxies, stars, planets, and life. But just like every other assumption we have made about the cosmos, this one was wrong. The Big Bang was not an explosion in space. It did not erupt into a void. It did not send debris flying outward the way a bomb would. And perhaps the most shocking revelation of all is this: there may never have been a before. To say we misunderstood the Big Bang is an understatement. We were not even close. The first mistake was imagining that the Big Bang happened in a location. It did not happen somewhere. It happened everywhere. Every point in the universe today was once part of that unimaginably dense, hot state. There was no center, no edge, no surrounding darkness. The universe did not expand into space. Space itself expanded. The Big Bang was the rapid stretching of space-time, not the detonation of matter exploding into a pre-existing vacuum. This distinction changes everything. It removes the idea of an outside. It removes the idea of a boundary. It removes the idea of a before. We were wrong to think of the Big Bang as a fireball. It was a transformation of the very fabric of reality. Another major misunderstanding came from the assumption that the universe began as a single, infinitely small point. Many people still imagine this singularity as the literal beginning, but that interpretation is becoming less believable. A singularity is a signal that our equations break, not a physical object. It is a gap in our understanding, not a moment in time. The singularity is a mathematical failure, not a real state of the universe. Most modern cosmologists believe the universe never reached infinite density. Instead, the early universe was simply very dense, dense beyond comprehension, but not infinitely so. This leads to the next shock. The Big Bang may not have been the beginning. This idea is profoundly unsettling. It means the question, what happened before the Big Bang, might not be unanswerable at all. It might simply require new physics. And that is exactly where modern theories lead us. For example, in eternal inflation theory, the universe is part of an ever-expanding multiverse. New universes constantly bubble out of the vacuum, each with its own laws of physics. Our Big Bang may have been one bubble forming in this larger foam. If so, then our universe has siblings, countless siblings, each with its own beginning. Another possibility is the bouncing universe model. In this picture, the universe did not start from nothing. Instead, a previous universe collapsed, shrank, approached a state of extreme density, and then rebounded into expansion. The Big Bang becomes a bounce, not a birth. Time did not begin at the Big Bang. It simply passed through a transition, a cosmic inhale followed by a cosmic exhale. Then there is the idea of a quantum beginning, a universe emerging from a fluctuation in a timeless quantum field. In this model, there is no before, not because time started at the Big Bang, but because time itself is not fundamental. Before the universe expands, time has no meaning. Asking what happened before the Big Bang becomes like asking what is north of the North Pole. The question collapses because the category collapses. We were wrong to assume time existed before the universe. Time may be a property of the universe, not the other way around. Another misconception about the Big Bang is the belief that it was noisy, explosive, and chaotic. But the early universe was astonishingly smooth, uniform, and quiet. The cosmic microwave background, the afterglow of the early universe, is nearly the same temperature everywhere. This uniformity should not exist. Regions of space too far apart to communicate share identical properties. The universe looks coordinated, as if different regions of space agreed on their conditions before there was any possibility of communication. This was a massive puzzle until inflation theory appeared. According to inflation, the universe expanded exponentially fast in an unimaginably tiny fraction of a second. So fast that quantum fluctuations were stretched across cosmic scales. Inflation smoothed the universe, flattened it, and set the initial conditions for everything that followed. But inflation is also bizarre. It predicts that space expands faster than light. It predicts that the observable universe is only a small patch of a much larger structure, and it predicts that inflation is eternal. If so, universes never stop being created. The Big Bang, instead of being the beginning, becomes a transition within a larger eternal process. We were wrong to think the Big Bang is the first page of reality. It may be a chapter in an infinite book. But even inflation creates new questions. It does not explain what caused inflation. It does not explain why inflation began or what triggered the universe to leave that state. It does not explain why inflation ended in this region, but continues elsewhere. Inflation solves some problems, but raises others. Then there's the biggest misunderstanding of all, the belief that the Big Bang explains the origin of matter. It does not. The Big Bang describes the evolution of the universe after the expansion begins. It does not describe the creation of matter or energy. In fact, the total energy of the universe may be zero. Gravity's negative energy may balance matter's positive energy. In this picture, the universe could emerge from nothing without violating physics. But this nothing is not nothing in the everyday sense. It is a quantum vacuum, a boiling sea of fluctuations, fields, and potential. We were wrong to think the universe popped out of absolute nothing. It emerged from a quantum state that defies ordinary language. There is another common misunderstanding, the belief that the universe started small and expanded into the giant cosmos we see today. But scale itself may be relative. Space-time could have stretched while quantum fields cooled. The Big Bang was not an outward movement into emptiness. It was a uniform stretching where all distances increased. Galaxies moved apart not because they were flung outward, but because the space between them expanded. And something even stranger, not only did space expand, but the expansion accelerates today. The universe is not coasting, it is speeding up, driven by dark energy. For reasons we do not understand, the universe wants to grow faster. The same physics that shaped the Big Bang still shapes the cosmos today. The universe is not finished expanding, it is still beginning. The old image of the Big Bang, a fiery explosion, is comforting because it makes sense to our minds. But the real story is almost incomprehensible. It involves quantum fluctuations, inflationary fields, vacuum energy, and the emergence of space-time itself. It is not simply physical. It is metaphysical. It challenges the boundary between something and nothing, between existence and non-existence, between time and timelessness. Perhaps the most unsettling truth is this: the Big Bang is not a single event. It is a process, a phase change, a transformation, and that transformation may happen endlessly in the multiverse. Our universe is one of many. Our Big Bang is one of many. Our laws of physics are one of many. And the reality we see is one possibility among infinite possibilities. We were wrong about the Big Bang because we tried to reduce it to something familiar. But the Big Bang is the least familiar thing imaginable. It is the moment when reality itself changed form, the moment when the universe learned how to exist. It is less an explosion and more a whisper of creation that echoed through the fabric of reality. And we have barely scratched its surface. We were wrong, and the more we learn, the more wrong we realize we were. But each mistake brings us closer. Each revision deepens the mystery. Each discovery expands the horizon. The Big Bang was not the beginning of everything. It was the beginning of us asking questions about everything. For many decades, dark matter was a placeholder, a name we gave to a mystery we could not explain. It began as a quiet whisper in the background of astrophysics, a subtle hint that something in our equations did not match the universe we observed. Galaxies rotated too fast. Clusters of galaxies clung together more tightly than gravity from visible matter could allow. Something unseen was holding everything together, something invisible, something massive, something that did not interact with light or radiation or any of the forces we understood. At first, scientists assumed it was just missing matter, faint stars, cold gas, rogue planets drifting through space, but each attempt to explain it with familiar objects failed, and gradually, the whisper grew into a roar. The universe was filled with matter we could not see. The reality was unavoidable. Most of the universe's mass was invisible, and this revelation changed everything. But the story of dark matter is not just about a missing ingredient. It is about how profoundly we misunderstood the universe. We assumed that what we see is what exists. We assumed galaxies were made mostly of stars, planets, gas, and dust. We assumed that gravity came from visible matter. But the universe had other plans. The cosmos revealed itself to be stranger, heavier, darker, and more complex than anyone imagined. And the deeper we searched, the more bewildering dark matter became. Because after nearly a century of investigation, after countless experiments, after satellites, detectors, colliders, telescopes, and massive underground chambers buried deep beneath mountains, we still do not know what dark matter is. We have ruled out almost every familiar possibility. We have tested every intuitive idea. And yet, the mystery persists. Dark matter is perhaps the greatest reminder that the universe does not care about our assumptions. The story began in the early 20th century, when astronomer Fritz Zwicky observed something alarming in the Coma cluster, a massive group of galaxies. The galaxies moved so quickly that they should have flown apart. There was not enough visible matter to hold them together. Zwicky calculated that the cluster needed far more mass than could be seen, more than 10 times as much. He called this missing mass dunkle Materie, or dark matter. But at the time, no one listened. His claims seemed too strange, too radical, too unbelievable. It would take decades before the science caught up to the observation. Years later, Vera Rubin studied the rotation of galaxies with far greater precision. Stars at the edges of galaxies move just as fast as stars near the center. This made no sense. In any system governed by gravity, objects farther from the center should move more slowly. Planets in the solar system follow this rule. Inner planets move fast, outer planets move slow. But galaxies did not obey this rule. The rotation curves were flat, and the only way to explain this was to accept the unthinkable. Galaxies are surrounded by enormous halos of invisible mass. The visible stars were only a tiny fraction of the true galaxy. The rest was unseen. By then, the evidence became overwhelming. Dark matter was not an anomaly. It was everywhere. It shaped galaxies, clusters, and the cosmic web itself. It determined how structures formed after the Big Bang. It sculpted the universe into its present form. Without dark matter, galaxies would not exist, stars would not form, life would never emerge. Dark matter is the scaffolding of the cosmos. It is the invisible architecture that holds the universe together. But knowing that dark matter exists is not the same as understanding it. And that's where the story becomes far stranger. We assumed dark matter was simply a new type of particle, something like a neutron or proton, but invisible. But as soon as we began searching for it, the universe mocked our assumptions. Detectors placed in deep underground caverns, shielded from cosmic rays, found nothing. After decades of searching for weakly interacting massive particles, once the leading candidates, we found no trace. Particle accelerators failed to produce dark matter in collisions. Dark matter did not appear in X-ray emissions. It did not appear in gamma rays. It did not appear in cosmic rays. It did not appear in neutrino experiments. Each failed attempt forced us to admit how wrong we were. We were wrong to think dark matter behaved like normal matter. It does not. We were wrong to think dark matter interacts through familiar forces. It does not. We were wrong to think dark matter would be easy to detect. It is not. We were wrong to think dark matter is a single type of particle. It might not be. Perhaps dark matter is made of an entire family of particles, a shadow realm of physics parallel to our own. Some theories propose that dark matter has its own forces, its own interactions, its own complex chemistry, not interacting with ours, but interacting with itself. If this is true, dark matter could form dark stars, dark planets, even dark galaxies composed entirely of unseen matter. A ghost cosmos woven into the one we see. We were wrong to assume dark matter is simple. Even more bizarre is the possibility that dark matter is not matter at all. Theories propose that dark matter is a manifestation of gravity behaving differently on cosmic scales. According to these modified gravity theories, we do not need invisible matter. We need a new theory of gravity. This idea remains controversial, but it highlights how deeply flawed our assumptions might be. Perhaps gravity itself changes across vast distances. Perhaps space-time behaves differently in the voids between galaxies. Perhaps Einstein's equations need correction. This is not science fiction. It is a serious scientific debate. Then there are the quantum possibilities. Perhaps dark matter consists of ultralight particles with wavelengths the size of galaxies. In this picture, galaxies float within giant waves, like boats bobbing on an invisible ocean. The waves create gravitational effects without forming clumps of matter. This could explain why dark matter does not collapse into disks like normal matter. It remains diffuse, spread out, ethereal. Or perhaps dark matter is made of axions, particles that barely interact with anything and fill space like a low-energy fog. Some experiments hint at their existence, but nothing is confirmed. Or perhaps dark matter is primordial black holes, tiny remnants from the early universe. But these too remain unproved. Every theory offers hope. Every theory collapses. Every experiment returns silence. Dark matter refuses to reveal itself. We often imagine science as a steady march toward truth, but dark matter shows that science is also a humbling confrontation with ignorance. We have mapped the influence of dark matter across billions of light years. We have measured its gravitational pull with exquisite precision. We have simulated its effect on cosmic evolution. We know exactly how much dark matter exists, and yet we cannot say what it is made of. We were wrong to believe seeing is believing. Most of the universe is invisible. The cosmic web, the vast structure connecting galaxies across the universe, is shaped entirely by dark matter. Without it, there would be no filaments, no clusters, no large-scale structure. Dark matter is the skeleton of the cosmos. Normal matter, stars, planets, nebulae, life, forms only on the scaffolding that dark matter provides. In this sense, dark matter is more real than the matter we can see. And then comes the deepest mystery of all. Dark matter may not be constant. Some theories propose that dark matter density changes over time. Others suggest that dark matter may decay, releasing energy slowly over billions of years. If so, the universe we see today is not the universe that existed billions of years ago. The dark matter halo around the Milky Way may be shrinking, or growing, or transforming. We have no way to know, yet. Even more unsettling is the possibility that dark matter is connected to dark energy, the force driving cosmic acceleration. Dark matter pulls, dark energy pushes. But what if they are two expressions of the same hidden physics, two faces of the same phenomenon? If so, then the entire dark sector, the unseen world that makes up most of the universe, may be governed by laws we have not even dreamed of. And here lies the ultimate shock. More than 80% of the universe's matter is dark matter, and more than 60% of its total energy is dark energy. That means everything we have ever studied, all atoms, stars, planets, galaxies, makes up less than 5% of the universe. We were wrong not just about dark matter. We were wrong about the universe itself. We thought we lived in a universe of stars. Instead, we live in a universe of shadows. We thought matter shaped the cosmos. Instead, invisible matter does. We thought we understood gravity. Instead, gravity reveals our ignorance. We thought the universe was built from the familiar. Instead, it is built from the unknown. And the most humbling truth is this: the universe works anyway. Dark matter does not care that we cannot see it. It holds galaxies together regardless. It sculpts the cosmic web without asking permission. It forms the structure of the universe while remaining hidden behind a curtain we cannot yet pull aside. We were wrong, but being wrong is not a failure. It is an invitation. Dark matter is not a void in our understanding. It is a doorway, a challenge from the universe itself, a reminder that the cosmos is not obligated to be simple or comfortable or visible. The universe is deeper than our assumptions, wider than our intuition, stranger than our imagination. And dark matter is proof that the universe has secrets we have not yet earned. For centuries, gravity was the king of the universe. It shaped the stars, it sculpted the galaxies, it commanded the dance of planets and moons. We believed it was the dominant force of creation, the architect of cosmic structure, the unseen hand that held everything together. And for a long time, that belief seemed unshakable. Gravity felt strong, mighty, absolute. But as always, the universe had a way of humbling us. Because one day, in one of the most shocking moments in the history of science, the universe quietly informed us that gravity is not the ruler we thought it was. Something else was at work. Something stronger, something stranger, something so powerful that it could overwhelm gravity on the largest scales imaginable. And the most disturbing part was this: we did not detect it by choice. It revealed itself by accident. Dark energy entered science as an unwanted guest, a contradiction, a nuisance, a problem. Astronomers studying distant supernovae expected one result. The universe should be slowing down. Gravity should be pulling everything inward. The expansion of space should be decelerating. But the supernovae told a different story. They were fainter than expected, farther away than they should have been. The universe was expanding faster than predicted, not slowing down, speeding up, growing at an accelerating rate. This discovery shocked the scientific world. It overturned decades of assumptions. It shattered everything we thought we knew about cosmic evolution. And it forced physicists to confront an impossible truth. Something in the universe was pushing galaxies apart. Gravity pulls. This mysterious force pushed. We gave this force a name, dark energy, but the name is a placeholder, a symbol for our ignorance. It does not describe what dark energy is, it only describes what it does. Dark energy is not a substance, at least not in any familiar sense. It does not clump. It does not gather. It does not interact with matter or light. It does not form structures. It does not live in galaxies. Instead, it permeates space uniformly. It fills the vacuum. It acts everywhere. It acts all the time. And its effect is to accelerate the expansion of the universe itself. The more space there is, the more dark energy there is. The more dark energy there is, the faster space expands. It is a runaway process, a cosmic pushing that grows stronger as the universe grows bigger. We were wrong to think the universe was slowing down. It is speeding up, and has been for billions of years. The first clue that dark energy might exist came from Einstein himself, long before the supernova studies. When Einstein formulated his theory of general relativity, he realized that a static universe, the universe people believed in at the time, was unstable. Gravity would eventually pull everything inward, causing collapse. To counteract this, Einstein added a term to his equations, the cosmological constant. It acted as a repulsive force, balancing gravity to keep the universe static. But when Edwin Hubble discovered that the universe was expanding, Einstein abandoned the cosmological constant, calling it his greatest mistake. He believed the universe had no need for such a term. But the universe had other ideas. Einstein's greatest mistake turned out to be one of his greatest insights. The cosmological constant is back, not to keep the universe static, but to explain why it accelerates. And now we know that this constant, or something like it, dominates the universe. Most of the universe's energy is dark energy. We were wrong to think matter is the primary ingredient of the cosmos. Matter, all atoms, all stars, all galaxies, makes up only a sliver of reality. Dark energy makes up the majority. The universe is not powered by matter, it is powered by the vacuum itself. And this is perhaps the most unsettling idea of all. Empty space has energy. The vacuum contributes pressure. The vacuum drives expansion. The vacuum shapes the universe. We were wrong to believe space is passive. Space is active. Space evolves. Space pushes. But what exactly is dark energy? The truth is that we do not know. There are several possibilities, and each one is more disturbing than the last. The simplest idea is that dark energy is Einstein's cosmological constant, a fixed energy of empty space. The vacuum contains energy that does not dilute as the universe expands. As space grows, the total amount of dark energy increases. This model predicts a universe that expands forever, faster and faster, until galaxies drift apart, stars burn out, matter decays, and the cosmos fades into cold darkness. A lonely, empty, featureless universe stretching into eternity. But this is only the simplest possibility, and nature rarely chooses the simple option. Another possibility is that dark energy is dynamic, that it changes over time. This model, the vacuum energy, is not constant but controlled by a field, similar to how electromagnetism is controlled by the electromagnetic field. This hypothetical field is called quintessence. If quintessence increases, the expansion accelerates even faster. If it decreases, expansion could slow. Quintessence could evolve. It could fluctuate. It could even disappear. The fate of the universe becomes uncertain. We do not know whether acceleration is permanent or temporary. The universe could change course suddenly on timescales billions of years long. We were wrong to think cosmic expansion is fixed. It may be dynamic. Yet another idea is far more terrifying. Dark energy may be a sign that the vacuum itself is unstable. In this scenario, the universe is sitting in a false vacuum, a metastable state. The vacuum energy we measure is temporary. One day, the vacuum could collapse into a lower state, rewriting the laws of physics instantly. Particles would change, forces would change, chemistry would change. Planets, stars, atoms, all would cease to exist as we know them. This vacuum collapse would expand at the speed of light, giving no warning. It would not be an explosion. It would be a transformation, a new universe overwriting the old. This possibility is not science fiction. It is a legitimate consequence of quantum field theory. We were wrong to assume the vacuum is safe. It may not be. Some physicists propose that dark energy is not a property of space at all, but a sign that our understanding of gravity is incomplete. Perhaps gravity weakens on large scales. Perhaps the equations governing cosmic structure break down across immense distances. If this is true, dark energy does not exist as a substance. It is simply the result of us using the wrong gravitational laws. This idea, modified gravity, is controversial, but it highlights our ignorance. We might be misinterpreting the behavior of the cosmos entirely. We were wrong to assume Einstein's equations are perfect. They may break at the edges of the universe. And then comes the most mind-bending idea. Dark energy may be connected to dark matter. They may be part of a hidden sector of physics. They may interact in ways we cannot detect. They may even transform into one another under extreme conditions. If the dark sector contains its own particles, fields, or interactions, then the universe could be filled with unseen processes shaping its evolution. Hidden forces, hidden structures, hidden physics. We were wrong to believe the universe has only one type of matter and one set of physical laws. It may have many. The deeper tragedy, or perhaps the deeper beauty, is that dark energy is invisible to every instrument we possess. We cannot detect it directly, we cannot measure it locally, we cannot bottle it, manipulate it, or observe it the way we observe particles or radiation. We only see its effect on the universe as a whole. Dark energy is not local, it is cosmic. It influences the universe on the grandest scales. It is the whisper of the vacuum speaking across billions of light years. And that whisper has consequences. As dark energy pushes galaxies apart, the sky will grow lonelier. Distant galaxies will fade beyond the cosmic horizon. One day, only the nearest galaxies, the ones gravitationally bound to us, will remain visible. Beyond that point, the rest of the universe will drift away faster than light. Not because they are moving through space faster than light, but because space is expanding faster than light between us. Eventually, the universe will become a dark ocean with islands of galaxies surrounded by infinite emptiness. For future civilizations, the universe will appear small, enclosed, isolated. They will have no way to know the cosmos was ever vast. Dark energy is slowly stealing the universe from us. And yet, as unsettling as this is, it reveals something profound. Our understanding of the universe is in its infancy. Dark energy forces us to confront how wrong we have been about space, time, and the forces that shape reality. It shows us that the universe is not driven primarily by matter. It is driven by something deeper, something stranger, something woven into the fabric of existence itself. We were wrong, but this is the cost of discovery. Each time the universe corrects us, it expands our imagination. Each time it humbles us, it enlarges our horizon. Dark energy is not just a problem to be solved. It is a doorway into new physics, new ideas, new realities. And whatever dark energy turns out to be, one truth is undeniable. The universe is not ruled by what we see. It is ruled by what we do not. For nearly all of human history, we believed the universe was everything, the totality, the whole, the complete collection of space, time, matter, and energy. The universe was the container of reality, and there was nothing beyond it, nothing outside it, nothing larger than it. That belief felt safe. It felt comforting. It felt final. But as our understanding deepened, as our telescopes peeled back cosmic layers, as our equations stretched into strange new territory, a radical truth began to emerge, a truth so unsettling that even scientists resisted it. The universe might not be the universe at all. It might be one universe among countless others. It might be a bubble in an infinite cosmic ocean. It might be one version of reality in a vast mosaic of realities. And all of our assumptions about everything might have been small-minded illusions born from our limited perspective. We were wrong to think there is only one universe. The seeds of this realization were planted when scientists discovered cosmic inflation, the theory that the universe expanded faster than the speed of light in a fraction of a second after the Big Bang. Inflation solved numerous puzzles. Why the universe is so smooth on large scales, why distant regions share the same temperature, why the universe appears flat rather than curved. But inflation came with an unexpected consequence, one that unsettles even the most hardened physicists. According to inflation theory, once inflation begins, it almost never ends everywhere at the same time. Instead, inflation continues eternally in most regions of space. Quantum fluctuations cause inflation to stop in small pockets, forming bubble universes. Our universe is one such bubble. Countless others are still forming. Inflation never stops. It keeps creating universe after universe after universe, forever. We were wrong to think the Big Bang was the beginning of everything. It was the beginning of our universe, not reality itself. In this picture, the multiverse is not a speculative fantasy. It is a natural consequence of cosmic evolution. The cosmos is not a single expanding bubble. It is a froth, a foam, a growing mosaic of universes, each isolated from the others by inflating space that expands too quickly for anything to cross. The universe we see is a tiny region of a far larger structure. And the most astonishing part is this. Each bubble universe can have different physical laws, different constants, different types of particles, different dimensions. The multiverse is not a collection of identical copies. It is a collection of possibilities. But the multiverse gets even stranger. Quantum mechanics, the theory governing the smallest scales, suggests that reality is not fixed but branching. Every time a quantum event occurs, every time a particle could be here or there, spin up or spin down, interact or not interact, the universe splits. Both outcomes happen. Both outcomes exist. Both outcomes are real. This is the many worlds interpretation. In this view, the universe is constantly dividing, producing endless branches of reality. There's a version of you reading this chapter, a version of you that never did, a version of you living a different life entirely, a version of the earth with a different history, infinite versions of everything, all existing simultaneously, separated not by distance, but by quantum states. We were wrong to think the universe is singular. Reality may be fractal, branching, endlessly multiplying. Then comes string theory, a theoretical framework that attempts to unify all the forces of nature. String theory proposes that the universe contains extra dimensions beyond the familiar three of space and one of time. These extra dimensions may be curled up, hidden, invisible to us, but they allow for the existence of higher dimensional objects known as brains. According to some versions of string theory, our universe is a three-dimensional brain floating in a higher dimensional space. Other brains drift nearby. When brains collide, they can create big bangs. Each collision births a universe. Universes may be created not once but repeatedly, collisions sparking new realms in an endless cycle. We were wrong to think the universe floats alone. It may be one, membrane in a cosmic sea of membranes. And there is yet another version, the holographic multiverse. According to the holographic principle, the universe may be a projection from information encoded on a lower dimensional surface. In this view, reality is not built from particles or fields, but from information woven into a cosmic boundary. And if each horizon, boundary, or surface encodes information differently, then each could generate a different universe. Reality becomes a vast library where each universe is a different book written by different rules. We were wrong to think reality must be three-dimensional. It may emerge from an information structure that transcends space itself. But what is perhaps most unsettling is the possibility that universes may interact. We have always assumed that other universes, if they exist, must be forever unreachable. But certain models suggest that universes may leave imprints on one another. When bubble universes collide, they can leave circular scars in the cosmic microwave background radiation. Some scientists have even searched for these signs. So far, the results are uncertain, but not impossible. If such a scar were found, it would mean our universe once bumped against another. Our cosmic bubble touched another realm. We were wrong to believe universes must be separate and isolated. Another idea emerges from quantum physics. The multiverse may be needed for our universe to be the way it is. Many of the constants in physics, the strength of gravity, the charge of the electron, the mass of fundamental particles, appear fine-tuned for life. Change them slightly and stars would never form, atoms would not hold together, chemical reactions would not occur, life would be impossible. Why do the constants have the values they do? Why does our universe permit complexity? The multiverse provides an answer. If countless universes exist, each with different physical laws, then we live in the one that allows life simply because life can only arise in universes that allow it. We were wrong to assume our universe is special. It may simply be one version among infinite variations. The multiverse also challenges our understanding of probability. If infinite universes exist, every possible event happens somewhere. Somewhere, a universe exists where you never existed. Somewhere, one exists where ancient civilizations evolved first. Somewhere, a universe exists where physics behaves in unimaginable ways, where gravity pushes instead of pulls, where time loops instead of flows, where stars are formed from exotic dark particles, where life emerges from physics different from anything we understand. We were wrong to assume the universe defines possibility. Possibility may be far broader than our universe. And yet, the multiverse is more than a scientific hypothesis. It is a philosophical earthquake. It forces us to confront the limits of human understanding. It forces us to reconsider the meaning of existence. It forces us to question whether reality is objective or layered. It forces us to accept that our universe may not be the main stage, but a small side room in an infinite mansion. We were wrong to believe the universe is the totality of existence. And if the multiverse is real, then the consequences are breathtaking. It means the Big Bang was not the birth of existence, but one moment in an eternal, ongoing process. It means that our universe may not be the most typical universe. We may live in a rare one. It means that deep space is not an empty expanse, but a boundary between realms. It means that science may never find the ultimate theory, because there may be no single set of fundamental laws. Each universe may have its own. It means that we may never understand the full structure of reality because we are trapped inside one universe, with senses built to perceive only one version of existence. But it also means something beautiful. It means the universe is more creative than we ever imagined. It means reality is richer than we ever believed. It means existence is far grander, stranger, and more infinite than the simple cosmos our ancestors gazed upon. We were wrong, but this kind of wrongness expands us. It enlarges our imagination. It invites us into a deeper awe. And perhaps most importantly, it reminds us that mystery is not a flaw in our understanding. It is the engine of discovery. The multiverse may not be provable today. It may not be provable tomorrow. But the very fact that our theories lead us there shows how far our perspective has grown. Once, humanity believed the universe was small. Then, we discovered galaxies. Then, we discovered the cosmic web. Then, we discovered expansion. Now, we face an even larger possibility. The universe may be infinite not only in size, but in number. For as long as we have existed, humans have been certain about one thing. Reality has limits, boundaries, edges, a horizon beyond which nothing lies. We believed the universe was the final container, the ultimate structure, the absolute totality of existence. But piece by piece, discovery by discovery, the universe has stripped that certainty away. It has shown us that space is not empty, that time does not flow as we believe, that gravity is not what it seems, that dark matter outweighs everything we see, that dark energy drives the expansion of existence itself, and that our universe may be only one among countless others. And with each revelation, one truth has become impossible to ignore. We were wrong about the limits of reality. We were wrong about where the universe ends. We were wrong about what is possible. We were wrong about the story we thought we were living inside. The end of this journey does not reveal a boundary. It reveals an opening, a door into mysteries even greater than the ones we have already uncovered. The first and most profound mistake we made was believing that the universe is obligated to reveal itself in terms we understand. We assume that reality must behave in ways that feel logical to a species living on a small planet, in a small solar system, in a small corner of a galaxy. But the universe does not exist to match our intuitions. Reality is not designed around human expectations. If anything, the history of science shows that every time our intuition meets the cosmos, intuition loses. Because the universe is not built from the logic of everyday experience. It is built from principles that transcend our senses, rules that operate on scales far beyond the human mind. Our next great error was believing that the universe has a fixed structure. We imagined it as a box, large, yes, but finite and unchanging in its rules. We thought physical laws were eternal. We thought constants were permanent. We thought dimensions were fixed. But modern physics paints a far stranger picture. It suggests that the laws of physics we see today may be temporary, emergent, the result of cooling processes after the Big Bang. In the early universe, forces may have been unified into one primordial interaction. As the universe expanded and cooled, symmetry broke and separate forces emerged. This means the laws of physics have a history. They may have a future. They may change. They may shift into new forms if the universe undergoes another phase transition. The constants of nature may not be constant at all. We were wrong to assume reality is static. Reality may evolve. Then came the discovery that reality is layered. On one layer, time flows. On another, it stands still. On one layer, space appears flat. On another, it is curved. On one layer, matter appears solid. On another, it is merely a vibration of fields. On one layer, particles obey classical logic. On another, they dissolve into quantum waves of probability. The universe contains hierarchies of truth. What is true on one scale becomes meaningless on another. What is solid on one scale becomes ghost-like on another. What appears simple at one level becomes chaos at the next. Reality is not one story. It is many stories woven together. We were wrong to believe the universe tells one narrative. It tells countless narratives, all interwoven. But perhaps the greatest misunderstanding of all was believing that the universe is independent of us, that we are observers standing outside of reality, watching it unfold from a safe distance. Quantum mechanics destroyed that illusion. It taught us that the act of observation affects the system being observed, that probability collapses into certainty only when measured, that the boundary between observer and observed is not as clear as we once thought. Consciousness does not create reality, but it plays a role in shaping what becomes real to us. And this raises an ancient question in a new form. How much of the universe is out there, and how much is a reflection of the limitations of the human mind? We were wrong to believe we stand apart from the universe. We are woven into it. As we stand at the edge of modern physics, something remarkable becomes clear. The universe has been peeling away our illusions one layer at a time. We thought the Earth was the center of existence. It was not. We thought the sun was the center. It was not. We thought the galaxy was the whole universe. It was not. We thought the universe was all that exists. It may not be. Every time we thought we found the boundary of reality, that boundary dissolved. The universe has repeatedly shown us that the edge is farther than we think. At one point, the edge of reality was the horizon. Then it became the edge of the solar system. Then the boundary of the Milky Way. Then the observable universe. Now the edge of reality may not be a physical location at all. It may be conceptual, it may be dimensional, it may be informational. The universe might not end at a spatial boundary, but at the limit of what physics can describe. Beyond that limit, reality might still exist, but it may be governed by laws we do not yet know, fields we cannot measure, dimensions we cannot perceive, or processes we cannot imagine. We were wrong to imagine the universe as something we could map like a continent. Reality may be infinite, in size, in form, in possibility. Consider the multiverse again. If countless universes exist, each with its own laws, then our universe is not the main universe. It is simply one expression of a deeper, more fundamental reality, a cosmic sea filled with islands of space-time. In that scenario, the real question is not, what is the universe, but what is the structure that gives rise to universes? The answer might lie in quantum fields that span higher dimensions. It might lie in the geometry of space-time, far beyond our four-dimensional perception. It might lie in patterns of information encoded at the deepest level of existence. The true reality may be the multiverse itself, or something even more abstract. We were wrong to think our universe is the fundamental building block. It may be the byproduct of a deeper layer of reality. Then there is the holographic principle, the idea that everything we see, everything we experience, everything that appears three-dimensional may be the projection of information encoded on a lower dimensional surface. If this is true, the universe is not what it appears. Space is not what it appears. Time is not what it appears. Reality becomes a shadow cast by a deeper informational world. And in that world, the limits we perceive may be illusions created by the way information is processed. We were wrong to assume the universe we see is the full universe. It may be a projection. Even more unsettling is the idea that reality might be emergent. Space might emerge from entanglement. Time might emerge from quantum correlation. Gravity might emerge from information flow. Particles might emerge from fields. Fields might emerge from geometry. Geometry might emerge from something deeper. Still, in this infinite cascade of emergence, what we call fundamental reality may not exist at all. Everything may be built upon something else. We were wrong to believe reality has a bottom. It may have endless layers beneath layers beneath layers. And yet, in all this vastness, in all this complexity, there is something profoundly hopeful. The deeper we look into the universe, the more connected everything becomes. Space-time connects matter. Gravity connects galaxies, quantum entanglement connects particles, information connects fields. Even universes in the multiverse may be connected by deeper laws. The cosmos is not a collection of isolated parts. It is a single unfolding process, rich with structure, woven with meaning, held together by unseen forces emerging from deeper truths. The greatest mistake we made was thinking the universe is separate from us. It is not. We are part of the process. We are expressions of the same physics that shaped stars. The atoms in our bones were forged in supernovae. The iron in our blood was hammered into existence in dying stars. The carbon that forms our cells was forged in the hearts of giants. We are not outsiders studying the universe. We are the universe studying itself. The cosmos gave rise to life, which gave rise to consciousness, which gave rise to curiosity. The most powerful force the universe has ever produced. The universe is not just what we observe. The universe is what we seek to understand. And as long as curiosity burns, the limits of reality will continue to expand. We were wrong, gloriously wrong, and we will be wrong again. That is the essence of discovery. The universe is not finished revealing itself. We are not finished learning. There are deeper layers waiting. Stranger truths waiting, new physics waiting, perhaps new forms of existence waiting. And the boundary we reach today will not be the boundary we know tomorrow. The universe is not small. Reality is not finite. Existence is not limited. The greatest lesson of all is this: the universe grows as we grow. It expands as our understanding expands. Its boundaries stretch as our imagination stretches. And whatever lies beyond the universe, whether other universes, higher dimensions, deeper structures, or something we cannot yet name, it is waiting for us. It has always been waiting.